Are we alone in the universe? This question has been intriguing humans for centuries. Since time immemorial, we've looked up to the stars, our curiosity piqued by the seemingly infinite cosmos. We've always wondered if somewhere in the vast expanse of space, there could be other beings looking back at us, pondering the same questions. The universe is mind-bogglingly vast. With billions of galaxies, each hosting billions of stars, the sheer scale is beyond human comprehension. It's a cosmic sea, filled with uncharted celestial bodies and phenomena. And in this enormous expanse, it seems almost implausible that Earth could be the only planet harboring life. Our curiosity, our thirst for knowledge, propels us to seek answers. It's led us to remarkable scientific theories and research, all aimed at understanding our place in the universe and finding signs of life beyond Earth. Today, we delve into the scientific theories and research related to the existence of extraterrestrial life. The Drake equation, formulated by Frank Drake in 1961, is a probabilistic argument to estimate the number of active extraterrestrial civilizations in the Milky Way. This equation is a mathematical tool to estimate the number of civilizations in our galaxy with whom we might be able to communicate. It's not a crystal ball that tells us the exact number, but a way of breaking down a complex question into smaller, more manageable parts. The Drake equation comprises 7 variables: the rate of star formation, the fraction of those stars with planetary systems, the number of planets that could potentially support life per planetary system, the fraction of those planets on which life actually appears, the fraction of life that evolves to become intelligent, the fraction of civilizations that develop a technology that releases detectable signs of their existence into space, and finally, the length of time such civilizations release detectable signals. Let's break it down a bit. The first variable, the rate of star formation, is something we have a pretty solid grasp on thanks to advancements in astronomy. The following 3 variables, however, are much trickier. They require us to make assumptions about things we can't directly observe, like the likelihood of life developing on a planet and the chances of that life becoming intelligent. The last 3 variables are even more speculative. They involve questions about the behavior and longevity of advanced civilizations, topics we can only theorize about. The Drake equation doesn't give us a definitive answer. It's more about the questions it raises. It forces us to think about the variables that would need to come into play for intelligent life to exist elsewhere in the universe. It's also important to remember that the equation only applies to our own galaxy, the Milky Way. There are billions of other galaxies out there, each with billions of stars and potentially even more planets. Despite its limitations, the Drake equation gives us a starting point to consider the possibility of life in the universe. So as we gaze up at the stars, we can't help but wonder, are we alone? But if there are a multitude of extraterrestrial civilizations, why haven't we encountered any? This is the Fermi Paradox. The Fermi Paradox is a scientific conundrum named after physicist Enrico Fermi. It arises from the apparent contradiction between the high probability estimates for the existence of extraterrestrial civilizations and the lack of evidence or contact with such civilizations. The paradox is based on a few key assumptions. The first is that our galaxy, with its roughly 200 billion stars, is teeming with planets. The second assumption is that on some of these planets, life has evolved into intelligent beings. The third assumption is that these beings have developed technology that allows them to explore and colonize space. If all these assumptions are correct, then the galaxy should be teeming with civilizations. But the big question remains, why haven't we encountered them? This is the crux of the Fermi Paradox. There are many proposed solutions to this paradox. Some suggest that intelligent life is rare or short-lived. Others propose that advanced civilizations are avoiding us or are simply not interested in contacting us. Yet others speculate that we are not listening properly or that we are not capable of detecting them with our current technology. Another solution is the zoo hypothesis, which suggests that Earth is deliberately isolated, like a zoo, with extraterrestrial civilizations observing us from a distance. The prime directive hypothesis proposes that extraterrestrial beings are following a policy of non-interference with lesser evolved civilizations. The Great Filter hypothesis is another fascinating proposition. It suggests that at some point in the evolution of a civilization, there's a significant barrier or filter that prevents further progress. If this filter is in our past, we are one of the lucky few who made it through. If it's in our future, however, we have yet to face our greatest challenge. The Fermi Paradox leaves us with more questions than answers about the existence of extraterrestrial life. The search for extraterrestrial intelligence, or SETI, is an organized effort to detect signals from alien civilizations. Born in the early 1960s, SETI is grounded in the scientific method and the belief that we are not alone in the universe. But how does one go about searching the cosmos for signs of life? SETI uses technologically advanced radio and optical telescopes to scan the skies for signals. The premise is simple. If there's an advanced civilization out there, they might be using radio waves, just as we do, to communicate or broadcast their existence. So, we listen, patiently and persistently, for any sign that could indicate we are not alone. SETI's methods are not just about passive listening, though. The project also encompasses active SETI, or METI, messaging to extraterrestrial intelligence. Here we flip the script and send our own signals into space, hoping someone or something might pick them up and respond. But despite these efforts, SETI has yet to find definitive proof of extraterrestrial life. There have been intriguing moments, though. The famous WOW signal, detected in 1977, remains unexplained. This strong radio signal, which lasted for 72 seconds, bore the hallmarks of extraterrestrial origin, but despite numerous attempts, it has never been detected again. Another notable event was the detection of fast radio bursts, or FRBs. These are millisecond-long flashes of radio light that come from beyond our galaxy. While most scientists believe they have a natural origin, the possibility of an artificial source has not been completely ruled out. So, where does SETI's lack of success leave us? Does it mean we are alone in the universe? Not necessarily. The cosmos is vast, and our search has barely scratched the surface. And remember, absence of evidence is not evidence of absence. SETI's search, while not yet fruitful, continues to fuel the hope of finding extraterrestrial life. The discovery of exoplanets, especially those in the Goldilocks zone, has given a new direction to the search for life. To understand why, let's first delve into what exoplanets are. Quite simply, exoplanets are planets that orbit stars outside of our solar system. Since the first confirmation of an exoplanet in the early 90s, we've discovered thousands more, each with their own unique characteristics, orbiting distant stars in far-flung corners of the galaxy. But what makes a planet special and potentially capable of harboring life is its location in what we call the Goldilocks zone. This term hails from the childhood tale of Goldilocks and the Three Bears, where the porridge wasn't too hot nor too cold, but just right. In the context of space, the Goldilocks zone refers to a habitable zone around a star where conditions could be just right, not too hot, not too cold, for life as we know it to exist. Planets within this zone have the potential for liquid water, a key ingredient for life, to exist on their surfaces. Too close to the star, and the planet would be a scorching wasteland. Too far, and it would be a frozen tundra. But, in that sweet spot, in the Goldilocks zone, life could potentially flourish. Now, just because a planet is in the Goldilocks zone doesn't guarantee it's teeming with life. There are many other factors at play, such as the planet's atmosphere, its geological activity, and much more. But the possibility is there, and that's what makes the discovery of these exoplanets so exciting. In the grand cosmic dance, these celestial bodies twirl around their stars, potentially harboring the answers to one of our most profound questions. Are we alone in the universe? Each new discovery of an exoplanet, particularly those nestled within their star's Goldilocks zone, brings us closer to an answer. The exploration of exoplanets brings us a step closer to possibly finding life beyond Earth. So, are we alone in the universe? This question, as ancient as our species itself, has led us down incredible paths of discovery. We've explored the Drake equation, pondering the probability of civilizations beyond our own. We've grappled with the Fermi Paradox, wrestling with the silence in a cosmos that seems ripe for life. Our journey took us to the efforts of SETI, the search for extraterrestrial intelligence, ever vigilant in their watch of the heavens. We then ventured to the exoplanets in the Goldilocks zone, places not too hot, not too cold, but just right for life as we know it. The universe is a vast, complex place filled with billions of galaxies, each with billions of stars. The sheer scale of it makes it hard to believe we are alone. Yet the search continues, our curiosity unsatisfied. While we may not have the definitive answer yet, the search for extraterrestrial life continues to be one of the most fascinating quests of mankind.